said, you have a geostationary satellite and it's looking down on the Earth. And it's looking for a bunch of different things, and there's actually a bunch of different things it can measure. One of the most important things is clouds. Going back to this image right here, the location of clouds help us identify the location of storm systems. And so we want to be able to identify where are clouds, how thick are they, how organized are they, because that then indicates a cyclonic system or some kind of organized weather system. And then what kind of precipitation do they have with them? So going back to this image, there's actually two ways that satellites do this. The first way is what's called a visible satellite image. Imagine if you were on the International Space Station and you were looking down towards the Earth and you see all the individual clouds and you see everything. Well, essentially that's what a visible satellite image is. It basically is just looking down and essentially getting a snapshot of the ground beneath it. Now, the way that it does this is it uses reflected solar radiation off of the clouds. So basically what happens is sunlight hits the cloud. So if you have a cloud here, I'll draw one. Okay. And let me pick a good color here. I'll pick a blue color. So let's say we have a cloud like this, very poorly drawn, but and then let's say we have some incoming sunlight. Let's see here. Let me undo that. Erased everything. Sorry about that. All right, so here's our cloud. So here's our cloud. And then here is our incoming sunlight. It hits the cloud, bounces back off the cloud, and then a satellite sensor, and let me draw one of those, a little satellite sensor, then appears and actually absorbs that radiation and measures that radiation. And then using that radiation, it can then say, okay, well, there's a lot of sunlight over at this moment, so this was likely a cloud, and very little sunlight reflected at this moment. Okay, that is land, and so on. And these visible satellite images actually have some pretty good positives to them. The biggest positive is that they are very detailed. Using a visible satellite image, you can actually see a ton of very cool details about storm systems, such as the eye of a hurricane. Visible satellite images actually really allow you to see the structure of a hurricane, to see the way that the eye is changing. Is it falling apart? Is it getting tighter? Is it getting larger? And that's just one thing, but they're very detailed. However, there are two main downfalls to visible satellites. The first one is visible satellites rely on reflected solar radiation. So that means that you need sunlight to hit a cloud and bounce off the cloud. This is only useful during the daytime. These satellites are essentially useless at night. They're essentially useless at night because there's no sunlight. And the other major downfall with these is that they rely on the amount of solar radiation reflected off an object to identify where clouds are. And there are some objects on the surface of the Earth, mainly ice and snow, that are just as reflective as clouds. And so oftentimes a visible satellite image can confuse snow or ice for a cloud. And so as meteorologists, we need to be able to discern the difference between snow and the difference between a cloud. And so it can get a little dicey there. Now, with that said, there are actually some technologies that make life a little bit easier when we don't have sunlight or when there's a lot of snow and the satellite image is confused. And these come in the form of what's called an infrared satellite. Now here's how this satellite works. Let me erase all of this. Oops. Let me erase all the ink. Okay, and let me pull up, wrong thing. Here we go. Sorry about that. Okay, so the other type of satellite image is what's called an infrared satellite image. Here's how this works. If you've ever taken my Met 10 class, or I would assume somebody else's Met 10 class, you've probably been introduced to some of the major concepts of radiation. If you haven't, let me just take a moment and just tell you a few important concepts. The first concept that you need to know is that all objects emit radiation. And in my lecture classes, I always love to do kind of an Oprah joke where I tell people that, hey, you're all emitting radiation. And it's true. We're all emitting radiation. But the type of radiation and the amount of radiation that we emit depends heavily on our temperature. And what's actually cool is that you can use a sensor, and you can even get one of these from Amazon for like 10 bucks. And using that sensor, you can actually measure the radiation an object is giving off and determine its temperature. Well, infrared satellites do the same thing. And what they do is, as they're flying over a cloud, so let me draw a little satellite here. Whoops, there we go. So here's a satellite here. Rather than relying on reflected sunlight, the way that these work is they instead rely on the infrared radiation that clouds give off. And clouds are typically colder than the ground below them. And the main reason why is because they're higher in elevation. They have a lot of condensed water, oftentimes a lot of ice, and so on. But another really useful fact about clouds is that the taller the cloud, the colder the cloud top. And so what an infrared satellite can actually do is, as it's flying over a cloud, it can use that cloud top temperature, how hot or cold it is, to say, okay, this is a high cloud, this is a low cloud, this is a really thick cloud, this is a really thin cloud. And that can actually give us a lot of information about, is there a cloud there? How high it is? How thick it is? And that can tell us a lot about what's going on inside the cloud. Now, there are a few strengths to this. So the first one is, because this doesn't rely on solar radiation, this is useful 24 hours a day. And so this actually allows us to view clouds at night using satellite technology. It's also a lot easier to distinguish clouds from snow. Typically, snow is a lot warmer, per se, than a cloud top. And the only weakness really is that it's not as detailed as visible satellites. And typically, meteorologists use a combination of these two, visible satellites and infrared satellites. So here's how a visible satellite image looks. This is actually taken a day after the visible satellite image I showed earlier. And just looking at it, you can identify some pretty major cloud locations. So let me pull up my laser pointer. Here we go. And as you can see, there's areas of relatively bright white, such as up here, such as down here, and over here. These represent pretty organized cloud systems. Meanwhile, where you see a lot of dark, such as down here and over here, these represent cloud-free areas. These represent areas with clear skies. And so this is pretty useful to us. This actually allows us to distinguish clouds from clear skies. Now, the negative of this is that a lot of regions, as I mentioned earlier, are usually pretty snow-covered. Over here's the Rocky Mountains, and there's a storm system just to the west of the Rocky Mountains, but much of this right here over the Rocky Mountains is actually snow cover. And so it's really hard to distinguish a storm system from snow cover. And then again, the other thing that I mentioned is that this is actually only useful during the daytime. And I'll actually show an image sort of proving that in a moment. All right, here is infrared satellite. Now, if you notice, infrared satellite uses a lot of color coding. These are actually what are called enhanced infrared satellites, and they rely on the cloud top temperature. And here's how they work. You see a lot of areas of kind of this milky grayish. These represent relatively warm cloud tops, and typically these are very low clouds, lots of fog, and very, very thin clouds. And so lots of this milky gray down here and then up here. These again represent low clouds. On the other hand, if you notice, there are these blues. These represent cooler clouds, so they're a little bit thicker and they're a little bit taller. And then the taller they get, the colder their cloud top gets. And so the colors then shift from blue to yellow and then sometimes orange and even red. And very, very tall clouds may even have red with them. Now, one of the reasons why we even care about how tall the cloud is typically the taller the cloud, the stronger the storm. Very tall clouds are clouds that are fed by what's called convection, and that allows them to have a lot of energy to them and a lot of stormy weather to them. All right, now moving on, there's a few things I wanted to talk about that are asked about in this lab, and so I just wanted to help you with that. So the first thing that's talked about a lot in this lab is what's called the subsolar point or subsatellite point. And the way this works is that you have a satellite and it's floating over a location and it's stationary over that location. And the subsatellite point simply is the point on Earth that is directly beneath the satellite. So for example, right here, if you take a look at these two images, the satellite is located right at this red star, and then the location of the Earth, or the location on Earth, directly beneath the satellite, is the subsatellite point. One of the questions that they ask is the concept of where sunlight is coming from, and also what time of day is the subsatellite point located at. So here's a few things you need to know. Imagine the Earth, and imagine that it's rotating like this. So basically this location, this subsatellite point, is actually moving further east. And these globes, this actually is just like any map that I've talked about. North is on the top, south is on the bottom, west is on the left, east is on the right. And this subsatellite point, as the Earth is rotating, it looks like it's traveling towards the east. Okay, so it looks like it's traveling towards the east. As a result of that, this subsatellite point is actually moving further and further into this area of daylight. And if you were to go back a few hours, this subsatellite point would have been located here over the dark area. So this is actually right after sunrise. Basically, what's just happened is, as the Earth is rotated, this subsatellite point has traveled, so now it's dark, 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 sunrise, 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 and now it's mid-morning. With that said,